Hello everyone, today we're going to talk about recorded detail. As far as the radiographic image is concerned, remember that the radiographic image is comprised of what we call photographic properties, which are density and contrast, and two geometric properties that are detail and distortion. When we say recorded detail, we're talking about the degree or how much geometric sharpness or accuracy of the structural lines are actually recorded in the image. When we look at the radiograph of the hip over on the right, we can see those little fine lines within the bone, that bony trabeculation. This would indicate that this radiograph has a higher degree of radiographic detail. It's a difficult concept to understand, but you can have an image that is actually 100% totally black and still have good detail on it. Doesn't make much sense. But if the correct factors of distance, your IR part alignment, your correct focal spot size, all of that were used, but you used too much KVP or too much mass, what are you doing? You're covering up the detail. If we were able to then subtract off that extra density, we would actually see the detail. So if we read an image that has excessive density or very poor contrast, has poor what we call visibility of detail. You can't see it. Poor visibility of detail. Yet it may have good detail. And once again, if the correct factors of distance, IR part alignment, correct focal spot size, all of those were used, but the KVP or the mass used was excessive, the detail of the structure on the radiograph is still present, but it's covered up, as I mentioned, by excessive density and cannot be viewed by the human eye. There's other terms for recorded detail. We can say definition, sharpness, spatial resolution, detail, all other terms for recorded detail. When we talk about film screen radiography, there is a test tool that can be used in which we can measure what are called line pairs per millimeter or cycles per millimeter. It's basically a piece of clear lucite into which has been embedded very thin lead lines, and these lead lines are set closer and closer and closer together. What you do is you take the tool, you put it on top of a cassette, and you basically radiograph it. So the tool is placed on a cassette, it's radiographed with technical factors that allow you, the radiographer, to visualize the images of the lead lines. You would get a radiograph just what looks like on the screen right now. And at the point where the lead lines are still seen as separate lines determines the line pairs per millimeter. You're going to get to a point when you're looking at this radiograph of this tool that the lines look like they're all blurred together. At that point where you can see the line still is separate, that would be the line pairs per millimeter, indicating the detail that you're able to see. Now, most humans can see no more than what we refer to as 5 line pairs per millimeter. But it's an interesting fact, radiographic films are actually able to capture even more detail than that, but we can't see it. In digital imaging, we refer to recorded detail more so with the term spatial resolution. And spatial resolution is determined by the pixel size, the matrix size, and what we call the gray scale bit depth. So down at the bottom of the image, you can see that we've got a drawing over on the right, which indicates pixels, which are the very front of what we call voxels. And when the pixels are in an arrangement, we refer to this as a matrix. So basically, when you're looking at this drawing, you can see that there would be an x-axis, a y-axis, and then your z-axis would give depth to the pixel itself. When we look at the top pictures, we can see that the picture A, a lot more crisp, a lot more clearer. In this the pixels would be smaller. You'd have more pixels in the matrix. B would be an example of poor detail or spatial resolution. The pixels are too big, and the image is starting to look very, very boxy. So when we say pixel stands for picture element. It's the individual boxes within the matrix. The matrix then is a series of boxes that give form to the image. And the grayscale bit depth is a number of shades of gray that that individual pixel can hold. And as I mentioned, when we look at the drawing over on the right at the bottom, you can see that there basically be three axes that would be involved. You'd have your x-axis, your y-axis, giving you your vertical and your horizontal presentation. And then we've got our z-axis, which then is going to give depth to the pixel itself. Digital imaging recorded detail is most commonly described in terms of spatial resolution. When there are slow changes in something, it's said to have low frequency. So slow changes in a wave, low frequency. When there are fast, abrupt changes, it's said to have a high frequency. Similarly, in the case of images, when we have a flat intensity region in an image, there's no or less changes in intensity, then that region is said to have low frequency. So basically what we're saying is the higher the frequency, the more detail can be recorded. Lower frequency, less detail would be recorded. So short wavelengths, high frequency, high resolution, long wavelengths, low frequency, low resolution. Now what are we talking about as far as wavelengths? Well, when the detector intercepts the X-ray photons, it's going to turn it into an electrical signal. And electrical signals travel as waves until they get to the computer. And when they get to the computer part of the system, then what's taken is these individual waves, and we look at certain points on the waves. Now, if the waves are very long wavelength, there's not a lot to look at. So we get low resolution. If the wavelengths are very close together, the computer can pick more points on these waves because you've got a greater amount of waves. Therefore, the computer can pick a greater number of points to look at. This is going to give you higher resolution. So this would be an example down below. In your digital class, you're going to talk more about pixel pitch, sampling, and so forth. But when we look at this, here we've got a low frequency wave. Okay, and how do I know it's low frequency? It's got a greater wavelength. And you can see the computer then, within a certain amount of time, is looking at certain points on the wave. These points are going to give the computer information. And when we look at this, then we can see on the low frequency compared to the high frequency, the computer is able to look at more of these waves or points on the wave. We'll talk more about this a little bit in this course, but like I said, you're going to talk much more about this in your digital imaging course. All radiographic images have less recorded detail than the object itself. We can do a pretty good job of imaging an anatomical part, but we're never going to get more detail than the object itself that we're radiographing. So the goal, though, is to create an image that has the best sharpness of detail, which we call umbra, and the least amount of unsharpness, which is penumbra. As I mentioned, the trabeculae of bone is an excellent guidepost to image resolution. If you can see the trabeculae, they're not blurred out, that's going to indicate good resolution, good detail. Remember, trabeculation over on the side here, it's that really that matrix that makes up the bone itself, these little individual lines that we're seeing here would be the inside, the spongy part of the bone, that trabeculation. And then how it is radiographed then, once again, here's that hip x-ray, and we can see those individual little fine lines. That's the bony trabeculation. There are a number of different measures of spatial resolution. Now, once again, you're going to talk much more about these in your digital imaging class. But the first one I want to mention that's pointed out in the book is point spread function. It's similar to penumbra if we're talking about film screen or conventional radiography. It's an expression of the boundaries of the image determined by a mathematical measurement of an image produced at a single point. That's a lot of verbiage, and what does it mean? Well, when we take a look at an image, we're taking a look at really individual little points, and these little points are put together very, very closely. If I have the point larger, and then I'm looking at the image, I'm not going to get as much detail. If I have fine little tiny points that are creating the image, I'm going to have better detail. So point spread, how is that single point? Is it spread out or is it more fine-tuned? Spatial frequency. High spatial resolution results from a high frequency signal, I mentioned that before, that is capable of imaging small objects. And modulation transfer function, or MTF, measures the accuracy of an image compared to the original object on a scale of 0 to 1. This is also referred to as fidelity. You may have heard of that term before, fidelity. An MTF of 1 would be a perfect image. That's what you strive for. You strive for an MTF of 1. You're not going to get an MTF of 1. That would be the absolute 100% perfect image. But that's what manufacturers strive for when they're creating the equipment to give you that perfect image. You've heard about the term noise before. We've talked about it. Noise, what is it? It's background information that the image receptor is receiving. Computers can do a pretty good job of filtering out that noise, but still in all, you're still going to always have some background information that you really don't want that's there. Quantum noise is another term for quantum model. And quantum model is that graininess that you see on an image. What causes it? It's a lack of sufficient incoming data for processing. The computer doesn't have enough information to process the image. Why doesn't it have enough information? It didn't have enough radiation photons that were striking the detector. The computer tries to formulate a good image, but it doesn't have enough information, so the image appears very grainy or blotchy looking. What's the cure? Whether you're talking about film screen radiography or you're talking about digital imaging radiography, if you've got a grainy, blotchy image, the cure is to give the detector more photons. And how are you going to do that? You're going to increase the mass. So you increase the number or quanta of the incoming signals by increasing the mass, allowing more photons to strike the detector. All digital imaging systems sample the incoming signal at discrete points, as I just mentioned. Here we have that drawing again. And there's something when we talk about digital imaging, and once again, I keep going back to this, but you'll talk more about this in your digital imaging class, something called Nyquist criterion. When we look at the wave, okay, a digital imaging system requires that the signal be sampled twice for each cycle. Now remember, a cycle is 2 alterations in a wave. So you have to sample, the computer has to sample the wave at least 2 times for there to be a decent looking image. If you have inadequate sampling occurring, which means that you didn't have the computer sampling at least twice, then you're going to have something called aliasing. Okay, and aliasing is going to give you a very strange looking or radiograph. It's an image with a visual impression of two slightly out of alignment images. We call this the Morier pattern. Okay, so point to get from this slide is that when we say Nyquist criterion, we're saying that the signal has to be looked at or sampled at least twice. The effects on image appearance. When fine detail is lacking, the image appears very blurry looking. And blurry images are not conducive to a good diagnosis. The radiologist is not going to be able to make a good diagnosis if he or she is looking at a blurry image. Factors affecting recorded detail. Resolution problems should be approached in the following order. You, the radiographer, should do everything that you can to try and eliminate motion. You always should reduce your OID, get that part as close to the image receptor as is possible. You always want to reduce your focal spot size. Always use the smallest focal spot size whenever you can. Now, of course, you're going to have limitations. If you're using a bigger or larger technique, you're not going to be able to use that small focal spot. But certainly, whenever you can, like on extremities, for example, you should use the small focal spot to give you the best detail. And you increase your SID. When you increase the SID, you get better detail. So let's talk about distance a little bit. So your best detail is when you have an increased SID and a decreased OID. Both decrease magnification, which will yield then better detail. So a larger SID and a smaller OID. For focal spot size, the major controlling factor of detail, because the smaller the focal spot, the less is the penumbra. You decrease the focal spot size, you decrease the penumbra. So you get your best detail with a small focal spot. Now there's actually a way or a formula, it's in your book, to calculate how much penumbra there actually is. So basically what you would do to calculate penumbra is you would take the size, actual size of the focal spot, you would multiply that by the OID that's used, and then you would divide that by the SOD, the source to object distance. Now remember, SID is from your tube to where your image is going to be captured. OID is from the object that you're radiographing to the image receptor. SOD would be from the tube to the object itself. So when we look at this drawing here, we can see when you're using a small focal spot, if you draw lines out from the end dimensions of the focal spot size, and then you go to the very edges, in this case of this bone here, you can see that geometrically when you're using a small focal spot, you're going to get less penumbra, that area that's kind of shaded in red there, or pink. When you use a larger focal spot size, you're going to get more penumbra. Digital systems, primary factors affecting recorded detail of digital imaging systems are the detector geometric properties itself and the image processing system. So for CR, computed radiography, you got decreased detail due to the photostimulable phosphor screens and the scanning system in the reader. With CR, basically what's happening is the image receptor is going to be capturing the X-ray photons, changing the components a little bit of the phosphors within the screen. You put that screen into the reader, it scans it with a laser, and light comes out, the light is captured, the light then is fed into the computer for processing. So you're involving light here, and anytime when you're using digital imaging, if light is going to be involved, it's kind of like a middleman, and that middleman kind of takes away some of the detail. So with DR, we've got two types of systems. You'll learn more about this in your digital imaging class as well. We've got indirect systems. Indirect systems, they use light to form the image. And once again, as I said, light is a middleman. That middleman takes away detail. There are systems that use an indirect component, and then we have systems that are direct systems. And they don't use any light to form the image. They're going to take those X-ray photons and turn them immediately into an electrical signal. With the indirect system, you've got the X-rays being captured. The X-rays are turning into light, and then the light is turning into an electrical signal. Once again, light, anytime you think of light as far as digital is concerned, you're going to lose detail. Okay, so these direct systems, they go from X-rays right into the electrical signal. Better detail. Remember motion. Anytime that you have motion, you're going to get decreased detail. And as far as motion is concerned, we've got voluntary motion. Voluntary motion is under the direct control of the patient. The patient can control it. The best way to get rid of voluntary motion is communication. Okay, telling your patient to stop moving, to stop breathing. We also have involuntary motion. Involuntary motion is not under the conscious control of the patient. The patient can't control it. The patient cannot tell him or her to stop their heart from beating, or his or her peristalsis to stop. Okay, so the only way to get rid of involuntary motion is short exposure times. Not rarely seen, but occasionally a problem would be equipment motion, and this would be due to an inadequate suspension system that holds the grid in place within the table. The cure for this would be an adequate suspension system. So if that grid, when it is reciprocating or moving, is not firmly held in place, that's when you could start to get some equipment motion. And then, of course, to stop motion, we also have immobilization techniques. Positioning tools are very helpful. We have sponges, sandbags can be used, pigostat, tape can also be used. We want to use those whenever possible. Of course, the worst immobilizers are humans themselves. They're a last resort. But if we had to choose a human immobilizer, we would always choose a male relative first. Males because they don't have any chance of being pregnant. Female relatives would be second, and non-radiology personnel would be third. Non-radiology personnel could be, for example, the nurse in the unit, for example. And a last resort then would be the radiographer, him or herself. And the reason for that is we're exposed to radiation all the time, so we would be the last resort. And I just want to thank Adler and Carlton. This is where the bulk of the material for this lecture came from.